This week, we're going to learn about actual, theoretical, and percent yield. And thankfully, this is something that you're already pretty familiar with the exception of possibly percent yield. These are just some newer definitions. So our notes today, these can go in the flipbook, or they can just simply be looked at and reviewed. Let's begin with some basic definitions first. Theoretical yield is actually something you've already done. You've done this in every single problem we've done so far. We're just putting a name to it. This is the calculated amount of product that will be formed. You're doing this all the time. We're just putting an official name to it. Something that's a little bit new to you will be something called actual yield. Now, if we were in class and every time we do a lab, the amount you get from a product from a lab experiment is the actual yield, and it's almost never equal to the theoretical yield. This is the amount of product obtained by experimental procedures, so you must actually perform the experiment and measure the final amount. The reason the actual yield is commonly not equal to the theoretical yield can be pretty broad. We'll discuss that in a little bit. The final one is percent yield. This is simply a ratio of actual divided by theoretical times 100%. This gives us an idea of how much we got versus how much we should have gotten. So why isn't every experiment or reaction 100% efficient? Well, there's a lot of factors from the method that you use. A lot of times we have very inefficient methods. We're always looking for ways to improve. It could be the purity of the chemicals and the reactants that you use, and it could be something known as entropy, which is a measure of disorder. Simply put, we rarely get everything that we'd expect to get. There's also a concern if we end up with something over 100% yield. Perhaps we made an unexpected product. That can be dangerous. Or maybe not all of the reactant reacted, and that can also be dangerous. So we always want to be careful we end up with over 100% yield. That tends to be more of a concern than if we don't get 100% yield. So here's our first example. Calcium carbonate can be decomposed in the presence of heat, and it will form calcium oxide and carbon dioxide. We have a balanced equation given to us already. Calcium carbonate decomposes in the presence of heat to make calcium oxide and also carbon dioxide. So our first question for this will be, what is the theoretical yield of calcium oxide if 24.8 grams of calcium carbonate was decomposed? There's no limiting reactant on this problem. We're just merely given 24.8 grams of calcium carbonate. This is a standard stoichiometry problem. You'll take your grams of calcium carbonate, you'll cancel grams of calcium carbonate and convert to moles of calcium carbonate. You'll cancel moles of calcium carbonate, convert to calcium oxide, and finally moles of calcium oxide converted to grams of calcium oxide. When you solve for this problem right here, you end up with 13.9 grams of calcium oxide. This is what you should get, the theoretical yield. So let's say we do this experiment in a laboratory. What is the percent yield of calcium oxide if 13.1 grams was produced in a lab? So clearly we didn't get everything we should have gotten. Remember that percent yield is actual yield over theoretical yield times 100%. My actual yield, what I got in the lab, was 13.1 grams. This is not calculated, this is measured. I calculated a theoretical percent of 13.9 grams. I take this sum, multiply by 100%, and I end up with 94.24% yield. It's pretty high. Most experiments really aren't that high. Now it's time to take a look at some of our homework. In problem number 1, we're given lithium hydroxide reacting with potassium chloride to yield lithium chloride and potassium hydroxide. This is already a balanced equation. It happens to be 1 to 1 to 1 to 1. First, we're given 20 grams of lithium hydroxide, and we're asked what is the theoretical yield of lithium chloride. This is a regular stoichiometric equation. Simply take 20 grams of lithium hydroxide, the amount we're given, and we're going to convert it to grams of lithium chloride. We're not told a specific amount for lithium chloride, so we can safely assume grams unless we're told otherwise. So let's set up the rest of our problem. Cancel grams of lithium hydroxide, and then convert to moles of lithium hydroxide. This is a standard molar equation. 1 mole of lithium hydroxide is equal to the molar mass of lithium hydroxide, which is around 24 grams. Next, I will cancel moles of lithium hydroxide and convert to moles of the chemical we're looking for, lithium chloride. This is a 1-to-1 ratio from the equation itself. And then I will go ahead and cancel moles of lithium chloride and convert them into grams of lithium chloride. This is another molar relationship. 1 mole equals a molar mass of lithium chloride, around 42.45 grams. Once I have my problem set up, remember it's always product of the top divided by product of the bottom. And the final amount is 35.38 grams of lithium chloride. This is the theoretical yield, what I should get of lithium chloride, assuming everything went well and was perfect. The next part of problem number 1, part B, we don't get the full amount. Yes, we're told that I produce around 6 grams of lithium chloride. This means I went into the laboratory, I did the experiment myself, and I only got 6 grams of the expected amount. So, what is the percent yield of this? Remember that percent yield is going to use a relatively simple formula, but it is new to us. It is the actual yield divided by the theoretical yield. Actual yield is what you got in a laboratory. Theoretical yield is what you calculated mathematically. Once these are gathered, you multiply the result by 100%, and that's your percent yield. 6 grams was my actual yield, and 35.38 was my theoretical yield. Once I divide these two, I'll multiply them by 100%, and the percent yield is about 16.96%. I didn't get anywhere near what I should have gotten for a variety of factors. I'm going to work on problem number 2 next over here. Here we're given C3H8 plus 5 oxygen, creating 3 CO2 and 4 water. This is a standard combustion reaction. If I start with 5 grams of C3H8, what is the theoretical yield of water? Okay, this is another standard stoichiometry equation. I'm going to take my grams of C3H8 and convert them into grams of water. Here, 5 grams of C3H8 is my starting point, and I will set up my dimensional analysis boxes. I'll cancel grams of C3H8 and convert them into moles of C3H8. This is a mole to gram conversion, where 1 mole equals a molar mass of C3H8, around 44 grams. In the next box, I will cancel moles of C3H8 and convert them into moles of water, what we're seeking. Because this is a mole-to-mole conversion, I have to use the balanced equation. The coefficient for C3H8 happens to be 1. The coefficient for water happens to be 4. In the next box, I'll go ahead and cancel moles of water, and I'll convert it into grams of water, a safe assumption if we're not told anything else. 1 mole is equal to around the molar mass of 18 grams of water. Product of the top divided by product of the bottom results in about 8.18 grams of water as my theoretical yield. This is the amount that I should get. Second part of question 2 is a little different. We're actually already given the percent yield. Here, it turns out the percent yield is 75%. So I went into the lab and I got a percent yield of 75%. I got 75% of what I should have gotten. Remember, I should have gotten 8.18 grams. So this problem is a tiny bit different than problem number 1. How many grams of water did I make? That's the question that's going to be asked over here. This is a minor rearrangement of the percent yield if we're already given it. If I take 8.18 grams of water, and I think about what is 75% of that, I should be able to find the actual yield. So let's do that. 8.18 grams of water, what I should have gotten, times 75%, which is the percent yield, will result in the actual yield of around 6.14 grams of water. It uses the same method that we learned, it's just a minor rearrangement of the formula. That's my final answer.